Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. And in today's lecture, we will be discussing the carry propagation and the adders. In the previous lecture, we discussed basic circuits of the adders, including the half adder and the full adder. Now we will be moving to the carry propagation concept in these adders. This was this circuit which we discussed in the last lecture. This was the representing the full adder. This full adder was designed using two half adders and one OR gate. We use this circuit to represent the addition of 3-bit numbers, one X, Y, and Z. All of them are 1 a bit. There is results are represented in form of two outputs. First one is the sum, and the second one is the carry. We also looked at if we have n-bit numbers, then how we can use this full adder to solve or add the n-bit numbers. We considered an example of a 4-bit adder in which we have two numbers a and b. Both of the numbers have 4 bits each from A0 to A3 and similarly from B0 to B3. We use the full adders to add each bit separately, just like we do on pen and paper. We solve it using, say, a column-wise approach. And from the first column, if a carry is generated, then that carry is added to the next 2-bit addition, and from that, if some carry is generated, this carry is added to the next full adder. And similarly, if the third full adder generates some carry, it will be added to the next full adder. And if there is a overall carry, then that would also be generated separately. Each bit here S0, S1, S2 and S3 represented the sum of the two numbers. We have seen that in this circuit, we can also assume that in the initial case or static case, the C0 is generally 0. So we can also represent this as just as the half adder, because it will be reduced to us just addition of the two bits A0 and the B0. So we can also replace this full adder by a half adder too. Okay, just assume that we are considering there is some C0 and its output will be generated in a form of S0 and C1. If you consider it that how long would it take to give the accurate result, then we have to understand the carry concept or the carry propagation concept in this whole system. We generally consider you can say the worst case scenario. Worst case scenario means that the carry is generated in all the columns, and for all the next columns you have to consider the carry bit too. So assume that for the first case, when the carry is generated after you can say the first cycle, because the A0 and B0 bits are available at the time of addition. Similarly, A1 and B1 bits are also available at the time of addition. A2, B2 are also available, and A3, B3 are also available for the addition. But this full adder, the second full adder, cannot perform its result till C1 is calculated accurately. So it has to wait till C1 is generated, only then it can produce the accurate result. Similarly, the next full adder, this one, cannot calculate its exact result till this C2 carry is generated. Similarly, this full adder cannot perform properly till this C3 carry is generated. It means that each of these full adder have to wait for their carry terms. This full adder, the second full adder, needs to wait for the C1. The third full adder needs to wait for the C2, and the fourth full adder needs to wait for the C3. Only then they can calculate their result. This process seems to be quite simple, but when you are going in terms of the implementation, you have to make your circuit as fast as possible. For this circuit, you have to wait till this C1, C2 and C3 are generated. Because the functionality of this is dependent upon the previous result. This full adder functionality is dependent on the previous full adder, and similarly this full adder functionality is determined on the previous one. So we need to carefully look at that how we can solve this carry propagation issue, because say this is a say 3-bit, a 4-bit adder. If we move it to the say 8-bit adder, then we will also have to add 4 more full adder, and then for the each of that full adder we have to wait for the previous carry to be generated. Only then we can accurately perform the addition. If you now consider this implementation of the full adder, we assume that each full adder here is implemented in this form, which involves 2 half adders and 1 OR gate. If you just assume that after this say first level, you can represent this circuit in this is the first level and this is the second level, and this becomes the third level. We can write it off: first level, second level implementation, and third level. So for the each full adder you have to pass through all these 3 levels. Just we assume here that say each gate has a 1 unit delay. Every type of gate, whether it's exclusive OR, AND, NOR, or OR gate, each of the gate has a delay of 1 unit. So it means that the result would be computed after say 3 units of time. Say if it is 1 millisecond, it means that after 3 millisecond correct result would be generated. Similarly, when we move to the next full adder, again there are the 3 level implementation here. So it would also require 3 levels here, similarly 3 here and 3 here. Some of the operations could be performed in parallel, like say because A naught, B naught, A1, B1, A2, B2, and A3, B3, they are all available at the time of addition when we start the addition process. So because this first half adder all represents only the 1 level representation, exclusive OR and the AND gate, so the first half adder process of all these 4 full adders could be performed in a single cycle. Say after 1 cycle we would have this expression from all the full adder, from this one, this one, this one, and this one. From the second, what we have to do is that because for the second level implementation of each full adder, if we assume here, it has to wait for the C naught or the carry in term, because it is dependent upon this carry term. So when its carry is ready, only then it will perform the next operation. So from here now on, after the first level, when all of them have performed this first step, the exclusive OR and the AND gate, then what would happen for the generation of carry? It would require 2 more levels, means 2 more unit delays, 2 and 3, because it has to be AND here, and then that result would require another OR here. So for carry to be generated from input to output, we may need about 2 delay for carry from to move from this part to this part. Similarly, when we are here, when carry is generated here, then from here C1 to C2, again we would require to move have 2 level delay here, 1 level here and 1 level for this one. Similarly, then we have to add the 2 levels here. So for when we have to perform the calculation of the last one, then it would also require the 2 level delay here too. So for the whole, if you see that for whole of this circuit, if just for the carry part only, we would require a 2, you can say a 2 cross 4 is equal to 8 gate level delay. You can say 8 gate level delay. We have assumed that when the first level is performed, all these addition are available. So it means that the total delay for calculating the sum would be 8 plus 1, means the 9 gate level delay would be required for this 4-bit adder to perform its addition process. In today's world, we require a faster system, and this system you can see is quite slow, because it has to wait about say 8 to 9 gate level delays. So there should be some mechanism so we can reduce this computation time, and we need to now view some other things or mechanism that how we could just minimize this whole time, because till now what we have done is that we have used the k maps and the other boolean algebra to minimize this circuit. Now we are moving to the other concept to minimizing or maximizing the speed of the circuit. There could be two kinds of techniques that could be applied to reduce this carry propagation delay. One thing is very clear that if we could develop a faster circuit, or you could say we could use a faster number of gates that have very low propagation delay, and we can always use them. But there are very limitations of the hardware, so the maximum or fastest gate we can use have a certain limitations. We cannot move above that. The other mechanism is that we define a certain kind of a mechanism in which we could calculate this carry in an advanced form, or we could predict or forecast this carry before the final implementation, so that we don't have to wait for the each full adder to compute its output. This mechanism is called the carry lookahead adder. Now we will look at the mechanism that how this circuit is used to perform the carry propagation thing. In this circuit, what we do is this is the circuit of a normal full adder, which we have seen in the slide before. What we do is instead of the Si and the Ci plus 1 term here, sorry, this is Ci plus 1. What we do here is that this for the sum and the carry term, we add in two intermediate variables in the system. We add two intermediate variable in the system. The first intermediate variable is known as this point. It is called, we call it as the pi, and this is known as the gi. The pi term here is called the carry propagate term, and the gi term here is known as the carry generate term, because this will determine that whether our carry will be propagated to the next half adder or not. So we are having here this AI, BI, and CI. The subscript I here is representing basically the bit number, just like we did the example. So it is representing, say, the A0 bits here or the A1 bit. So it will be representing the appropriate level here. Similarly, this will be representing the sum bits Si, and this Ci plus 1 will be representing the next carry that would be generated for the next cascaded full adder. So if you write the equations of all these terms, they are very simple, because this is just the exclusive OR. So we can easily write it here as like this. The next is the AND one, which is representing the GI term here. The final output of this full adder is represented by SI, which you can clearly see is the exclusive OR operation of this carry propagate term and the carry in from the previous or the carry in from the previous full adder. Similarly, the next carry is generated, which is represented Ci plus 1. You have to remember this, because this is the next carry that is to be generated here. This is basically OR of this operation and this one, these two AND gates. This is the OR of these two ones. So it is represented here as Gi plus Pi into Ci. So this is the carry term here. Now we have to define a mechanism by which we can reduce this propagation delay of this carry generation term. If you look at this, just the calculate the C, or putting I is equal to 0 term here. If you just put I equal to 0, then in this equation, then what we would get here is we will get C1 here. This would become G0, this would become P0, and that would become C0. So C0 is the basically the starting carry or the main carry in of the whole adder. So it is represented by the C0 bit. And now from the similar mechanism, if you calculate the C2 term, means instead of the here I was equal to 0. Now if you put I equal to 1 here in this, then we would get the carry generation equal to C2 here, and the rest equation will become from here G1 plus P1 to C1. Now if you look at this equation, in this equation it is dependent upon this carry term, the C1 term. And if you look at more deeply, then you can see that this carry one is already generated or can be generated through the equation which was calculated here for I equal to 0. So if you just put the value of C1 here, it means after P1 we put the value of C naught here, then we would get this term here. So you can see that when we are in the level 1 or I is equal to 1, it means we are at the basically at the second full adder of the cascaded series. And in this series, now we are no more dependent upon the C1 term. We are only dependent on the C0 term. Look, it's only C0 term now because we have put the value that is the C1 here. And if you calculate the value of the C1, the value of all the values here, the rest of the values here means the P0 terms and the G0 terms, they are all already calculated because for the each cycle, this first half adder terms are already calculated simultaneously. So after the first cycle, you have the values of the P0, P1, P2, P3 available to you. Similarly, you have the value of G0, G1, G2 and G3 available to you. So this carry is dependent upon only the G0 and the P0 which are already calculated. So we just put the values. So our C2 term is now also dependent upon the C0 instead of the C1 term. Similarly, if you move on to the third full adder, then in the case of the third full adder, then you have a general equation from this one which have included this C2 term here because it is dependent upon the carry generated from the previous stage. Now if you closely look at this one, this carry is also generated from the previous equation. And if you just put the value of the previous equation, which was actually this equation, and you put the value here C2, so we would have the final result equal to this one. So this is the result which is only dependent on the C0 value. Look at this. It's only dependent upon the C0. We are at a stage 3 or the full adder stage 3 and we are only dependent upon the C0 value. We are not dependent upon the C1 or the C2 because this is, as you can say, a recursive process in which the value of C1 is dependent upon C0. We can represent it in terms of C0. Similarly, we could also represent C2 in terms of C1 or C0. So we have represented all the carries that are need to be generated in a form of C0. So it is not dependent upon any now dependent upon the C1 or the C2 terms. It is only dependent upon the initial carry which was defined as the C0. Now what we need to do is we need to represent or express these three equations C1, C2, C3 and similarly C4. C4 is similar equation, just we will have a few more terms, so I've just not written here, but it will be calculated in the similar manner. So what we need to do is we need to represent these C1, C2, C3s in form of a certain circuit, or what circuit would be just implementing these equations, this equation, this equation and this equation. And you can see that all these three equations are in a sum of product form, so that they could easily be implemented in a two-level diagram. So if you represent all these equations, the C1, C2, C3 which we have just written, you can represent them in a two-level diagram. This is the first level and this is the second level. So we can represent it in a form of a two-level diagram. So but the important thing is here is that there is an additionality of the circuit here in the system, but we have also be able to generate the carry in advance. So we are no longer dependent upon the C1, C2 and the C3 terms separately. We can just using the two level extra gate delay, we can calculate the C1, C2 and C3 terms in the advance. So that would really help us in calculating or generating the overall system response much more faster. So this is the actual carry propagation term here. Now what we would do is we would simply, you can say, just put it inside and say a block diagram or an IC form. Say this will we will put it in a, say, this kind of a block where P2 G2 P1 G1 and P0 G0 C0 would become the input of the system, and C3 C2 and C would one would become the output of the system. So this is the extra circuit now associated with our adder. It is called the carry propagation circuit, and we have would implement this circuit inside this block diagram. So this block diagram circuit it has the, or this IC you can say has this circuit which is implemented in the last slide. So now what we need to do is, now we would have to add the other things or the other parts of the system to represent the carry processes, so that we could represent what our system is, or the addition process, how the addition process looks like here. So what we do is, now if you look at this, this is the actually the first half adder circuit of each of the full adder in the cascaded system. The example that we are dealing here is the 4 bit adder system, and this is represents the first half adders of each of these 4 adders. Now each of these term will generate the P3 carry propagate and the carry generate terms, and these terms will be fed to this system, which represents the carry look ahead generation, which we discussed in the last slide. And that circuit would produce the following things: the carry output, the C4 C3 C2 and the C1. And the next result, the final result would be generated here, as because the last carry would be the C4, which would be generated in the same way we have generated the C3. The sum of the bit, say A3 and B3, would be generated as this one. In this case, the S3 case, we are having the exclusive OR operation. This is actually representing the, you can say, the second full adder of the whole full adder system. And this is the P3 term here, means that this is actually, this term is joined here. Similarly, this P2 term is, you can say, it is joined from here. And similarly, the P1 is joined here and P0 is joined here. So in this case, you can see that we could easily represent this system, and what we will get here is that from S0, S1, S2 and S3 we will get the sum product from here, while for this whole term we would get the carry term from here. So now if you have to measure the overall gate level delay that is required to represent this summation process or the addition process, then how we could calculate that? Because if you remember, if you use the full adder in the 4 cascaded form, then we ended up in a, say, 9 gate level delay at that time, and we assume that each gate is representing a unit delay, so you can assume that there was 9 unit delay to perform the full addition process. Now in this way we will now look at that how this look ahead cadder is useful in reducing this computation time. So for this half adder of the system, we will have, you can say, a 1 level gate delay here, and we have already seen in the previous slide that this whole system or the circuitry inside it basically represents the two gate level delay, means that it would be representing the two gates here, because it was representing the sum of product here. So that would require the one level for the AND gates and the one level for the OR gate. So we would have a 2 unit delay here. And then in the last one, there's an exclusive OR gate only, so that would be representing the 1 unit here. So in total, to get the complete result, we would be requiring, say, 4 unit delay for this system. We are assuming here that all gates are representing in a, say, a unit delay, or the propagation delay of all each gate is 1 unit. So you can see that the previous circuit of the 4-bit full adder was a cascaded system, was giving the complete result in 9 units, or you can say if 1 unit is equal to 1 millisecond, it was giving the result in 9 milliseconds, while this carry look adder circuit is giving the result in form of 4 unit delays. So we have added the extra complexity in form of the hardware here, because we have added all these steps involved in this block here as the extra circuitry to it. But we are also achieving a better result in terms of the speed of the system. So in this way, our parallel addition is performed, and we have been able to achieve a better or less delay of the system. Now we will discuss a little bit about the half subtractor or the subtractor circuit. We know that if you follow the same routine of the as of the half adder and the full adder, then we could also define the half subtractor as having the two inputs x and y, and its output would be the difference and the borrow terms. So if you are representing a half adder, that would require a 2-bit system. So for the 2 bits, we are representing here as x and the y here. Its result are represented in the form of the difference and the borrow term. We have already discussed how we have achieved this one. And if you clearly look at this system and define a separate or design a circuit for this, then we could have design a separate circuit for this difference and the borrow term here. The difference term could be represented in a form of AND OR gate in here. We are assuming here that we are having the both of the inputs in complemented and the uncomplemented form. So we would get the difference here, and we would get the borrow result as here. And if you closely look at this difference, then you can see that this difference is representing the exclusive OR operation of the 2-bit system. So we can also represent this difference circuit in a form of just a simple exclusive OR like this one. And the next is just the AND operation, in which one of the inputs, the first input is inverted. So we can also represent the half subtractor circuit using just an exclusive OR and the addition of an AND gate. Now if we move on to the full subtractor thing, and the full subtractor, we are assuming that we have an input from the previous column or the borrow from the previous column too. So what we need to do this is, now we have to consider a 3-bit system or 3-bit subtraction process. Again, we are representing the outputs in form of disturbance and the borrow from the next one. So first, what we do is that we represent all these terms here as the combination in term of minterms form, you can say. So we will have a 3-bit system, so we are representing the 8 different combinations here. And depending upon the values of each of these bit, we write here as the truth table for the difference one and the borrow one. And now what we need to do is we need to design a circuit for this full subtractor system. We can assume this D as the separate input and this B as also the separate input for the system. And then for each of the system, what we do is we design a K-map. So for the first, what we do is for the D, we design a K-map. If you see this K-map, then all the ones, there are 4 ones here, but none of the one is in the form of the adjacent scale. Each one is representing a different say box here, which is not adjacent to any other one. So there could not be a further minimization to this circuit. So what we need to do is we need to represent the difference in form of these four minterms. For the borrow term, we could have a combination of three different adjacent ones in the form of boxes. Because we have ones at the M1, M3, M2, and M7. We could combine this M3 and M7, and then we could combine M1 and M3 and M3 and M2. This would give us three terms of 2 literals each. So the borrow would be represented here as this one. Now if you just represent them in the form of a circuit diagram, we would be representing this as the difference term here, and this would be representing here as the borrow term. And if you see that in both of them, we are assuming here that we are having both or all the inputs in the form of both the complemented and the uncomplemented form. Oh, we have seen the full subtractor and the half subtractor circuits, but if you remember when we discussed the arithmetics or the binary arithmetics, we said that we use the or prefer the complement process in this whole system or the subtraction process, because the complement process offered a much better solution to the subtraction process. And we discussed at that time that there could be a single circuit that could be used for both the adder and the subtraction process. So now what we will be doing here is we will be modifying the adder circuit that we have discussed just now to make it work as a subtractor too. And how we can make it as a subtractor, you know that for the subtraction process, if it is signed or unsigned number, we have to know it in the advance. So otherwise the operation of the two bits are the is same. How we are dealing is we will discuss it later, that whether the number is signed or the unsigned one. What we do here is that we will using a simple circuit. There you can see that this circuit is the same that was used for the addition process. We have only done few modifications in it to make it as a subtractor. And how we have done is that because if you have to subtract the b, say, from a, then what we need to do is we need to calculate the 2's complement of the b term here. And how we calculate this 2's complement of the b here is that we what we do is that we first takes the one's complement, and then what we do is we add 1 in it to compute the 2's complement of the system. If you see the system, we have a input here m, which is representing the mode of the system. When m is equal to 0, the circuit behaves as an adder. When m is equal to 0, this circuits behave as an adder when we perform the simple addition or the a plus b term. And when this circuit is having a value of m is equal to 1, then in that case this circuit becomes a subtractor, and it performs basically the addition of the or subtraction of the term, or you can say it would do the a minus b term. And how we can use it, that uh, first what we need to understand is that say we have to subtract the a minus b term. So if we have m is equal to 0, then in that case this circuit would be behaving like a normal adder. In that case, what would happen at the output of this exclusive OR gate, this one, and this one? We know that when m is equal to 0, we would be having a term like this, say b exclusive OR 0. And you know from the identities of the exclusive OR that we discussed in a few lectures back, it would give us b. So when m is equal to 0, we would get the same term here, means we would get the b naught here, b1 here, b2 here, and b3 here. And when m is equal to 1, then what would happen here is that we would be having this term here, b exclusive OR 1. And if you remember, this is equal to the b complement terms, mean we would be getting the complement term here, here, and here. So if B3 is 1 here, then we would be getting the B3 equal to 0 here. If say B2 is equal to 0 here, then that we would be getting the it equal to V1. Once we will get the complement term here, then important thing is that how we are going to calculate the two's complement, because if we are complementing these terms here, it is only generating the one's complement. But for the subtraction process, we require the two's complement thing. So in that case, this C naught helps us in doing that, because for the normal case, if you remember, we discussed that this full adder case, normal addition case, this C naught is generally equal to 0. So we can also replace it as a half adder. But we have kept it as a full adder for a purpose, and that purpose is that if we use here C naught with M is equal to 1, then basically that 1 is doing the addition process. So we are first complementing them using these exclusive OR gates, and then when M is equal to 1, we would get a C0 equal to 1, which is equal to adding a 1 in the 1's complement form. So it would give us the result in the form of the 2's complement form. And then in the similar way, we will perform this process, and we would get the result in the 4 bits form S1, S0, S1, S2, and S3. While if there is some carry generated, then that would be represented in a form of this carry bit here for the unsigned case. For the signed case, what we have to do is that we have to also, or for the both of the cases, for the signed and the unsigned cases, there is an other thing that is representing, or the other output that is represented here as V. Actually, V is representing here as the overflow condition, or the overflow flag. The final output would be generated for the subtraction process as in the form of these 4 bits and with the carry term. While there is an other extra term that is also output in this, that is also the output in this system, that is the overflow system. The overflow system is very important, and it represents that whether our result is inside the limits of the bits or it is exceeding that bit. Because if you remember, we have discussed that if we are adding any two numbers, then their result could be representing, say, two n bit number, then their result could be represented in n plus 1 bit. So when we solve this thing in the on pen and paper, then it's not a problem for us, because we keep on adding the extra columns here. But when we are dealing with the hardware or the digital systems, then in that case we need to be very careful that what is the register size, or that how much computation our processor could perform. Say if a processor could perform as a 4-bit processor, then it needs to perform the addition in within the 4-bit. It cannot represent the result in the form of the carry, which generally acts as an extra bit. So if the result is carry is generated, it means that it is that our result is becoming an overflow, or it is representing in more than 4 bits. So we need to have some process or mechanism by which we could show that there is overflow in the system, that our result is more than 4 bits. So we can inform the user or the system that there is an overflow that has occurred in our system. Generally, because our system is fixed length system, so we will be only be dealing with the result that is representing in these 4 bits S0, S1, S2, and S3. We could not be using this bit. So how does this overflow flags works? First, we need to know that when this carry or overflow would be generated, because there are certain condition of this. Say if we are subtracting two numbers, then in that case, we would probably not get this carry or the overflow term here, because an overflow cannot occur after addition if one number is positive and the other one is negative. Since you can say that adding a positive number to a negative number would produce a result whose magnitude would definitely be less than the larger of the two. So in that case, there would not overflow occur. But if the both of the numbers are the positive or both number are negative, then only then the overflow would occur. First, we would consider the case of the unsigned number. In the unsigned number, it's very simple that if we have, say, the last carry equal to 1, means say C is equal to 1, then we could say that the overflow has occurred. This is for the unsigned case only. But for the signed case, it is a little bit different, because for the signed case, we use the extra bit to represent the sign, and we also include that bit in the whole of the addition and the subtraction process. So if the two carries that are applied to, say, an exclusive or gate, then its output could be representing the overflow that would occur in an signed number addition, or say if for the signed number subtraction, if both of the number are represented in their 2's complement form. So for signed number case, we have to check two things, that if they are different, then only then we would be equal to 1, indicating the overflow. For the signed case, we would be equal to 1 when this carry and the carry generated in the last bit and the carry generated out from the last four ladder, both of them are compared. If both of them have equal or have say different values, one is 0 and one is 1, then in that case we would have b equal to 1. Otherwise, if both of them are same, then we would have b is equal to 0, which would be indicating that there is no overflow occur in the system. In both cases, if the overflow occur or not, the actual result would be only be representing in these 4 bit. Only in the case of the overflow, we would be getting indication from this one, if in the case of the signed one, and from this one, from in the case of unsigned one, that our result may not be suitable, because it is not represented in the appropriate number of bits. Kindly do follow these pages for better understanding, and do read these topics specifically, because they are a little more complex than what we have discussed so far. I would suggest you to definitely read these pages for better understanding. Thank you.